In this video in our Chemistry of the P-block series, we are going to be taking a look at the redox properties of the compounds in this part of the periodic table. That is, whether or not these compounds behave as reducing agents or oxidizing agents. So we're going to focus in particularly on group 4 of the P-block here. And group 4 is quite an unusual group in the sense that we get non-metals towards the top of the group, in carbon, but by the time we reach lead at the bottom of the group, we're down into metal territory. And so we do see a large difference from the top to the bottom of group 4, more so probably than any other group in the periodic table. And as a result, it's a group that's revisited quite often in our chemistry. Now here we're going to look at the differences in terms of redox properties. So we're going to look at the stable oxidation states of the compounds formed by these elements. So if we think of carbon, stable oxidation states of carbon is +4. An example of that is carbon dioxide. So if we just pause for a second here to remind ourselves of what oxidation states are all about. So if we draw ourselves a carbon dioxide molecule here, so CO2. Now, oxygen, if you recall, has an oxidation state primarily of -2. So there are two oxygens here. So those two together would come to -4. Now, if you recall also, when we add the oxidation states together of a compound, then the oxidation states should come to 0. So therefore, in order to get this to 0, carbon here must be in an oxidation state of +4. That's what we're referring to here in that table. Carbon's stable oxidation state is +4. So the stable oxide for carbon is CO2. As we go down the group, we find silicon is a similar situation. Silicon's stable oxide for silicon is SiO2, +4 oxidation state. Same for germanium and same for tin. But when we reach the bottom of the group for lead, we see a change there. On the bottom of group 4, the stable oxidation state is +2. PbO, lead oxide, lead 2 oxide, is the stable oxide for lead. So that is a definite change from the top of the group. Now, these elements will also form other oxides, which are less stable, unstable oxides. And let's take a look at those. So if we look at carbon, carbon can also form carbon monoxide, CO. If we remind ourselves again of the oxidation states there, CO, get that back into black, CO, oxygen is one oxygen here now, and that's going to be in oxidation state -2 for the oxygen. And therefore, for the carbon to bring the oxidation states to 0 in total is going to be +2. So carbon monoxide is an unstable oxide of carbon, and it's in a +2 oxidation state. Now, thankfully, carbon hardly ever forms carbon monoxide, as it's a very poisonous gas. Carbon dioxide is a stable oxide for carbon, but it can potentially form a carbon monoxide and be in an oxidation state of +2. Silicon does not form any other oxides other than SiO2, so there are no unstable oxidation states for silicon oxide. Germanium, again, similar to carbon, germanium 2 oxide is an unstable oxide of germanium. It does exist, but it's unstable. Tin oxide, tin 2 oxide, SNO, is also an unstable oxide of tin. Again, it does exist, but it's unstable. And for lead, the unstable oxidation state this time is lead 4 oxide. So it's PbO2 is a lead oxide compound that does exist, but it's unstable and quite reactive. So towards the top of group 4 then, the stable oxidation state are +4, and for the bottom of group 4, the stable oxidation state is going to be +2. However, we're not that interested in these stable oxides. We're more interested in the unstable oxides because these are the ones that tend to react. Now, the unstable oxide reactivity for carbon Carbon monoxide, because it's unstable in oxidation state +2 and it wants to become CO2 with oxidation state +4, in so doing it gets oxidized itself. Therefore it will act as a reducing agent. It will reduce other compounds, and we'll look at that in a shortly. By the time we get to the bottom of the group, however, the lead, unstable oxidation state +4, lead 4 oxide, wants to become lead 2 oxide. It wants to be reduced itself, and in so doing it behaves as an oxidizing agent. And so lead 4 oxide is quite reactive and behaves to oxidize other compounds, and we'll take a look at that. So what we're going to focus on now then, in the next couple of slides, is we're going to look at how carbon monoxide behaves as reducing agents. What is the bonding in carbon monoxide and how it behaves as a reducing agent. We're also going to look at the bonding in lead 4 oxide and how that behaves as an oxidizing agent. Okay, so let's take a look at carbon first of all then. So the stable oxide of carbon is CO2, and we can take a look at the bonding there. So we've ignored the 1s electrons here because they're not engaged in bonding. So carbon will be 2s2 and 2p2. And as we've seen previously in these videos now, we know that carbon can form 4 covalent bonds. And in order to do that, it needs to promote the 2s electron to the 2p. Now it's in a position where it can form 4 covalent bonds. It's going to do that with 2 oxygens. So each oxygen has to bring in a pair of electrons and form a double bond. And so here they come. 2 electrons from one oxygen, 2 electrons from another oxygen. Carbon forms CO2 with 8 electrons in its outer shell. It's obeying our octet rule and it's forming a nice stable compound CO2. Nice and stable and unreactive. We're not that interested in CO2 in this part of the course though. We're far more interested in carbon monoxide because that is an unstable oxide of carbon and therefore it's going to be reactive. So if we look at the bonding in carbon monoxide then, now carbon again is going to start where we started previously, 2s2 and 2p2. This time the 2s electrons here are not going to engage in bonding. We do not get the promotion that we got earlier. What needs to happen here is that carbon is going to form a double bond with these 2 electrons, and then it's going to rely on oxygen bringing in an extra pair of electrons via a coordinate bond here. So carbon is going to bond with 1 oxygen with a double bond, and then the other pair of electrons are going to have to be supplied by oxygen in the form of a coordinate bond. So if we take a look at that in terms of a dot cross diagram, and think how that might look. Get ourselves on a new page. Then draw ourselves a nice big carbon here, and we'll put an oxygen next to it here. So if we show the electrons in carbon as dots, so there are 4 of them. So there's 1, 2, I'll put another 2 here. And oxygens will show as crosses. So we'll have 1 electron pairing up here, another one pairing up here. Now oxygen's got 6 electrons in its outer shell, so there's 4 of them right there. Now if you notice, carbon so far at the moment has only got 6 electrons in its outer shell. It's electron deficient at the moment. Whereas oxygen, it has another pair of electrons which we haven't drawn yet, so oxygen would be up to 8. However, in order to get carbon up to 8 as well, the oxygen has to supply those other 2 electrons and allow carbon to share them in a coordinate bond. And that would be a single covalent bond and another single covalent bond. So there's almost like a triple bond that existing in carbon monoxide here. Now that is not a stable situation for carbon to be in, much more stable for it to be in an oxidation state of +4, where the s electron is being used for bonding here. For carbon monoxide, this s electron is not being used for bonding, and if you remember from our previous videos, if they're not used for bonding, these s electrons are referred to as an inert pair, And this is the inert pair effect coming into action here. And if we go back to our dot cross diagram, we can show the inert pair over here. This is the pair of electrons that are not engaged in bonding. These are our s electrons. Now, in this part of the periodic table, high up in group 4, it's very unusual for the inert pair effect to be seen occurring. And as a result, carbon monoxide is a rare oxide of carbon. However, when it does form, it's very reactive and it can act as a reducing agent. And it can reduce other compounds such as iron oxide. If you remember your work from the blast furnace at GCSE, iron oxide is reduced by carbon monoxide into iron. The benefit for carbon monoxide is that it gets oxidized itself to carbon dioxide. So carbon in the +2 oxidation state, unstable. Carbon in the +4 oxidation state, stable. So high up in group 4 then, the +4 oxidation state is the nice stable compounds. The +2 oxidation state, where we see the inert pair effect, is unusual, it's unstable, it doesn't often happen, and when it does happen, it's very reactive and it will act as reducing agents. Okay, so if we dive down to the bottom of group 4 then and take a look at lead. Now, if you recall from our table earlier, lead 2 oxide now is the stable oxidation state for lead, PbO, not PbO2. Now, if we look at the bonding that's occurring here, now notice this time now we're in 6s and 6p territory. We're in the 6th period here of the periodic table, 6th energy level for lead, 6s2, 6p2. Now, we're a long way away from the nucleus here, so it's more stable for lead to actually lose these 2 electrons completely. And in so doing, it forms a lead 2+ ion. Those electrons will be given to oxygen to form an O2- ion, and they will bond ionically Pb2+ and O2-. And if you think about it, that makes sense. Lead is a metal at the bottom of group 4. Oxygen is a non-metal. Metals and non-metals will tend to form ionic compounds. And this is the stable situation for lead to be in with oxygen to form lead 2 oxide. Notice, excuse me, notice here we have the 6s electrons not being utilized for bonding, and therefore they're referred to as the inert pair. And at the bottom of group 4 rather, this is what we tend to see happening more often. We tend to see the inert pair effect coming into play. Very rare for it to happen at the top of group 4. That's why carbon hardly ever does this, but lead does it consistently, and we tend to find lead 2 compounds as being the stable compounds for lead. However, stable tends to mean non-reactive, and we're not that interested in them. We're far more interested in compounds which are reactive, like lead 4 oxide. Now, this is a rare oxide for lead. It will form, but it's unstable when it does so, and it wants to react. So let's take a look at the bonding in lead 4 oxide then. So again, we're 6s2 and 6p2. So in this situation, we're going to get promotion of the 6 electron to the 6p orbital, and we're going to get bonding with 2 oxygens. Again, 2 oxygens bringing in 2 electrons each, a double bond forming between each one, and so we're forming a covalent compound here. Now, this is, based on our GCSE rules even, this would be strange, a metal and a non-metal forming a covalent oxide. Not what we'd expect at all. And indeed, it's a very rare situation for this to happen. But when it does happen, the compound tends to be unstable and therefore reactive. When it does react, it wants to go from lead in the +4 oxidation state to lead in the +2 oxidation state. It wants to get reduced. If it gets reduced, then it must oxidize something else, and therefore lead 4 oxide tends to act as an oxidizing agent. And if you react it with something like concentrated hydrochloric acid, that will tend to form PbCl2. So lead in +4 oxidation state has become lead in the +2 oxidation state. This is far more stable. This would be an ionic compound between lead and chlorine. Chlorine is also formed, So if you think of the chlorine here in HCl, it would be in a -1 oxidation state. Now it's in a 0 oxidation state. The chlorine's been oxidized. Therefore, the lead 4 oxide has behaved as an oxidizing agent. Okay then, so back to our table to summarize then. So we have just looked at the reaction of carbon acting as, or carbon monoxide rather, acting as a reducing agent. And we've also looked at the reaction of lead 4 oxide acting as an oxidizing agent. So you need to be aware of the fact that at the top of the group here, the stable oxidation state tends to be +4. We tend to see the s electron being used for bonding. We tend to see the compounds being being covalent rather in their nature. Towards the bottom of group 4, excuse me, the compounds tend to be, the stable compounds tend to be ionic in their nature. Lead 2 oxide is an ionic compound. Unstable compound of lead would be the covalent version, lead 4 oxide. That's unstable, and when it does form, it acts as an oxidizing agent. In comparison to the unstable oxide of carbon, which is CO, carbon monoxide, it's still covalent, but it's a very strained form of carbon and oxygen bonding together, much more stable if we can revert back to carbon in the +4 oxidation state. So, inert pair effect being quite common down here in lead, being very rare up here in carbon. So lots going on there in terms of redox in group 4. Unstable oxidation states at the top being reducing agents, unstable oxidation states at the bottom being oxidizing agents. You need to be able to understand why that happens. You need to be able to explain how the inert pair effect gets more common as we come down the group, and you need to understand and be able to explain how they are reducing agents at the top and the unstable oxides are oxidizing agents at the bottom of the group. So fill in your booklets and make sure you answer lots of questions on this because it's a very common exam question.